hand over the microphone to Professor Groome, who is the Emeritus Professor at Oxford Brookes University. He developed the original inhibin A and inhibin B assays, and as both Marion and I said, he developed the antibodies that are used in the most commonly used AMH assays throughout the world. So,
thank you very much. My goals are at this late time of the day, after you've had a busy tiring day, is to send you home quickly, happily, satisfied, and to try and also give you some comments which you may find helpful in looking at. Now, it should be easy for me to give you a clear overview, because I'm not burdened by an excessive knowledge of other areas of endocrinology. I'm going to be very focused on AMH. I have an axe to grind, because for 10 years these antibodies have been waiting to get out in the assays that they deserve. And now you see some of the quality of the automated assays which have been presented today. Any hormone which can stop a boy from developing a vagina and a uterus, and at a later time help a woman count her eggs, is deserved of the greatest respect. That's a personal opinion. Here's the man we owe it to. He would be very, very proud of what is going on. AMH is a molecule you can explain to your friends and your family what you're doing every day, because it relates to everyday life. But what does it do? It was originally discovered as an endocrine hormone, making the Müllerian duct regress and the vagina and the uterus go away in boys. But as I will explain in the next few slides, it is not an endocrine hormone for the ovary in women. There's no evidence that blood AMH has any effect on the ovary whatsoever. This is a knockout mouse that does not make AMH. On this knockout mouse is based our whole understanding of what AMH does. The male has testes and makes sperm, but it also has a uterus, coming back to Young's original discovery. But in the ovary, the female has more growing follicles, loses fertility at a younger age. I was the first person with axeltemin to develop an assay with this pair of antibodies, again to measure AMH in mice. And we measured the AMH in mice of various ages. At 18 months, they had their menopause. And axeltemin called it the mousepause. So the AMH mouse was also a valuable tool to me. When I wanted to make really brilliant antibodies to AMH, I used knockout mice. Why? Because human AMH and mouse AMH are so similar that if you immunize ordinary mice, lots of the epitopes you can't get antibodies to. So I chose to use knockout mice. You will note that exactly the same strategy has appeared in one of the recent papers by the ANCH group. There's a separate section following on from a paper by David Robertson, which explains that they use knockout mouse. Knockout mouse is the best thing to use to make antibodies to AMH. And this is another finding from the paper with axeltemin at that time. There's the decline in AMH, there's the decline in follicles. The most important thing is that there is a good correlation between primordial follicles and the growing follicles. So this was the basis for understanding that if you measure AMH in humans, although you're measuring growing follicles, there's going to be a direct correlation with primordial follicles. Now I'm going to do what I used to do in lectures in my university. When I've got too many slides for the time available, I resort to sort of manual mode. So what I'm going to be over here is I'm going to be a primordial follicle. Now, AMH in the blood has nothing to do with primordial follicles because primordial follicles don't have a blood supply. The follicle then at some point decides it's going to grow. Why does it grow? Well, the evidence suggests that AMH is stopping it from growing by inhibiting various growth factors. And according to a paper only a few weeks ago, that oocyte, when it's ready, when it's decided it wants to grow, produces a protein called GREM2. And GREM2 neutralizes the AMH in its environment. And then the follicle is awakened, it grows. So it starts to grow. As it grows, AMH starts appearing in the follicle. By the time the follicle is about 8 millimetres diameter, it's got its maximum level of AMH. And the AMH is feeding back as a brake on follicular development. But here's interestingly, the concentration of AMH in small follicles is 1,000 nanogram per mil. Why on earth is a few nanogram per million blood going to be affecting it? So up till now, AMH in the blood has not been doing anything in the ovary. It's the ovarian environment. There's a lot of evidence that AMH diffuses around the stroma. So the AMH, which is keeping the primordial follicles inactive, is actually coming from the follicular environment, not from the blood. So then the follicle comes up towards the stage where a dominant follicle is going to be selected. And it then starts to decline. And so people think that the correct follicular selection involves FSH, it involves AMH. What is the AMH doing? How is it keeping a brake on follicular development? It's inhibiting aromatase. It's a brake on estradiol production. But at some point, selection takes place, the dominant follicle goes on, AMH is then declining. In the pre-ovulatory follicle, there's very little AMH at all being made anymore. But it then starts to be made like a cumulus cells around the oocyte. And there's quite a bit of evidence that at that late stage, AMH from the cumulus helps the egg in its final meiotic divisions. And there's quite a lot of evidence coming out that if you measure AMH in the follicle fluid at the time of aspiration, the AMH in some way relates to egg quality. And people have shown that if you mature eggs in vitro, if you add AMH to the medium, it helps the egg to develop. So, in all of those things, AMH is not an endocrine hormone for the ovary. The AMH in the ovary is doing paracrine jobs, and further research on the function of AMH should not be on the blood, it should be on the ovary. It should be at these various stages. How does it block follicular development? How does it block primordial follicular awakening? How does it get involved in the growth of the follicle? How is it involved in follicular selection, the dominant follicle? How is it involved in the cumulus? And more importantly, why is it that in PCOS, people say, Stephen Frank published a paper showing that in PCOS small follicles, there was an underexpression of AMH. That could be allowed more follicles to grow. And he's also shown, or others have shown, that the normal decline in AMH, which takes place as the follicle gets bigger, actually does not take place in PCOS. And this has been linked in some ways to LH and the link between LH. So basically, I'll come back to my slides because I could carry on forever like that, but AMH is not an endocrine hormone acting on the ovary. This is a nice little slide. I find that as I put this talk together, a lot of the slides, I'd made the monoclonal antibodies which were actually used in the staining. That's stained for GDF9 in the oocyte, very, very important molecule, involved in twinning and various other things. Let's strip by this is the concentrations of AMH in follicular fluid. See now, why would 2 or 3 nanograms per million of blood be affecting that follicle with 1,000 nanograms per million of its own? It would be nonsense, wouldn't it? So, coming on now past all these things, there's the paper in Nielsen et al. Showing how the GREM2 protein neutralizes AMH and enables the primordial follicle to awake. Coming on, this is a paper by Stephen Franks showing that AMH is expressed in granulosa cells of all stage follicles, but is deficient in PCOS. One thing that AMH is definitely involved in is that this is a paper from Faddy showing that the decline in the number of follicles in the female ovary accelerates when the woman gets to 40. And this is probably because, even if you want to find an explanation for it, it's probably because once the body's decided that its peak reproductive period is over and it's likely to be producing bad quality eggs anyway, it thinks I'll jack it in rather than just uniformly fade away. And the way that takes place is that because of the declining number of small follicles, inhibin B is going to be smaller. That's going to allow FSH to rise to drive the follicles faster, and AMH, the brake is coming off as well. So that's why these things are all involved in the accelerated decline in fertility which takes place around about 40. So AMH is in there with the best of them. Now, what about clinical applications of AMH? Well, we know that it's very useful in the diagnosis of cryptorchidism. If there's a normal testis, but it's just in the wrong position, the AMH levels can be normal. We know that it's very useful in the diagnosis of intersex disorders. We know that in women, it's got all these applications. Predicting time to menopause, optimizing IVF, you heard the Roche talk today. Very, very important to predict the age of menopause because of all the subsidiary risks of loss of bone density, increased cardiovascular risk, endometrial cancer risk. Now, what do we need for all these clinical applications? I'm not dwelling on those because you know them. AMH doesn't have an endocrine role probably in the ovary, but there's quite a lot of intriguing evidence that in men it does have a role. In knockout mice, for example, knockout mice, the knockout male minus knockout mice have a disinterest compared to normal male mice in pheromones from female mice. And the group in New Zealand who believe that AMH levels, the higher AMH levels in boys, the young boys, affect brain development and relate to autism. So, and there are receptors, there are type 2 receptors for AMH on cardiovascular tissue and in the brain. So, if AMH is an endocrine hormone, it's not acting on the ovary, it's acting on these other organs. So it's not moving. It's not, oh yes it is, right. Right, so you've got these wonderful clinical applications. What's stopping you? What's stopping you going for them? Well, look at the, never mind assays, look at all these variations. Age, ethnicity, smoking, contraception, circadian variation. One of the speakers I heard today said there wasn't circadian variation, but he's quite wrong because there are 2 papers on it and one recent paper showing that in PCOS patients have the, I can't remember which way round it was. I think it was PCOS patients had circadian variation and normal people didn't, or the other way around. So there's intra-cycle variation, there's inter-cycle variation, there's the knowledge that vitamin D deficiency can lower AMH levels, we know chemotherapy for cancer can lower levels, there's the time of year which may work through vitamin D can change levels, there's obesity which can act through leptin, because leptin affects the AMH promoter, there's PCOS where levels go up. There's enough sources of variation which you need to take into account to establish a normal range before you start an assay variation. So the bottom line is that the assays have to be perfect, really, because you can't really address all these things with the variations that we've had so far. So all the evidence suggests that sensitive, robust, well-standardized AMH assays that are automated would find an immediate place in clinical research and valuable practice. You don't need to measure something different, you just need to measure a bit more sensitivity and a lot more reliability. There are no special outstanding problems which apply to the assay of this molecule. AMH is an easy analyte. Inhibin A was difficult. My goodness, with Inhibin A, when the first antibodies had to be made, there was no recombinant available. There were all sorts of interferences that I didn't understand, so I started boiling the samples to get rid of the interferences. There's none of these problems with AMH. It's a perfectly straightforward, stable analyte. So what's AMH structure? I've drawn it. Doesn't might look much like an AMH molecule. I've drawn it in a linear form. It's really much more globular than that. So this is AMH. It's a 270,000 molecular weight chains, identical state chains. It's a homodimer. In that form, it's called uncleaved pro-AMH or non-bioactive AMH. In that form, it doesn't bind its receptor. In the cell, it undergoes a cleavage by a furin-type protease, which is a member of a family called subtilisin-like endoproteases. It cleaved at one particular bond to generate what is called cleaved AMH-NC or bioactive AMH, and this can bind the receptor. It's going to be very similar in structure to so the 2 molecules are very similar in structure. The second one is bioactive. As I shall explain to you later, both circulate in blood in approximately equal amounts, and I'm going to, in some detail, I'm going to go in a few minutes to say to you which form should you be measuring and is it likely to make any difference. Now, when I was first sent recombinant AMH by Axel Temmen, I made a pair of antibodies, which you can see here. Sorry, is this a pointer?
No.
There's no pointer, okay. So you can see the pair of antibodies there, 9, 6 and 2, 6. And you can see that they're reacting with the pro region of the molecule. But you can see that the 9,6 antibody doesn't react with this form. This is because in those days, Actyltemon's recombinant AMH and other recombinant AMH, they had a secondary proteolysis site, and that stopped the second antibody binding. So the first antibody pair I sent to DSL to set up their assays, they came back to me after about 3 months, they said, we can't work this, the recombinant standard is unstable. And not only that, it doesn't recognise rats or other species. So I went back and I got another aliquot of my frozen in mouse spleen out of the freezer. I did another fusion, and I made the pair which are now used in Gen 2. That we now know that one of those recognises the mature region, one recognises the pro region. Earlier thoughts that there was some recognition of the pro region, of the mature region by both, was because that one Axel's preparation had some fragments of the molecule which were created by this second proteolysis site, and one of them had the misfortune of migrating at the same molecular weight as mature. So I'll show you the evidence that what we now. So now, why does AMH have a mature region? Or sorry, why does it have a pro region? The pro region does two things. Firstly, it helps the mature region fold correctly during synthesis, but more importantly, it increases the serum half-life. The half-life of the intact AMH is 28 hours, but typically TGF-beta family mature regions would have a half-life of just a few minutes. And AMHC, the mature region of AMH, is very sticky, and it would no doubt get lost. Cleavage by furin-like proteases is nothing unusual. Remember the inhibin family molecule? When you measure inhibin A, you're measuring all those different size forms of inhibin A. So, is that percentage cleavage of any significance? Is it controlled? Is it important? No. It just happens. Nobody has ever found any particular control of cleavage of these TGF-beta family members. It just seems to be a feature of the molecule. So one would have to find additional arguments for why one would want to measure one form rather than another. All the evidence is that if the ovary or any part of the body wants to increase the amount of AMH in the ovary at any one time, it does it by changes in gene synthesis. For example, leptin and AMH. Leptin has an effect on the AMH promoter. Vitamin D has an effect on the AMH promoter, and estradiol has an effect through estrogen receptor beta on the AMH receptor. There's no evidence at all that the percentage of the total AMH which is bioactive is A, variable, B, significant, or D, A, B, or C, regulated. Right, so what's the specificity of the Gen 2 pair? This is a block from Actyltemon when we had when we understood the banding pattern a little bit more, and the conclusion from that is that the capture antibody recognises the mature region, the detection antibody recognises the pro region, and also a fragment of the pro region, which is formed by this secondary cleavage. But one thing that you may not realise, but the Gen 2 and Access antibodies are exactly the same antibody pair that are used in the Roche assay. So they've now got quite a good pedigree, and this supports the use of both parties in that we now agree that there are no stability problems. There's another block recently, independent confirmation of the specificity of the antibodies. This was Pankhurst, New Zealand paper. He actually took a Gen 2 AMH plate, and into the well he put some recombinant pro-AMH, and then he eluted and he blotted to see what he got. So you can see that it actually captures, if you add AMHC, the C-terminal mature region, to the well, it's captured. So that confirms the fact that the capture antibody on the plate captures through the C-terminus, and here it captures the whole molecule. And he also goes on to show that there is no reactivity with, go back. He also goes on to show that there's no reactivity in the assay of free mature or free pro-regions. Now this is in terms of the stability of AMH, when all these problems arose, it made me ill because people were saying AMH is unstable, there's conformational change, it's being degraded proteolytically, there's disulfide exchange, there's oxidation, every conceivable thing. Let me show you how stable AMH is. In 2004, Axel Temin sent me a preparation of his recombinant AMH, which he said was 30 micrograms per mil. I was using a standard material, AMH preparation from Biogen, from Richard Kate, and I measured his material, and when it arrived in my lab, I assayed it, and instead of giving 30, which Axel told me it was, it gave 2.5. And when I incubated it at room temperature for another week, it went down to 0.1. That was with my old antibody pair that recognised the probe. But with the Gen 2 pair, it should have been 30. When I measured it, to start with, it was 29.4. And after a week at 37, it was 30. So basically, the Gen 2 antibody pair is indifferent to the primary and the secondary proteolysis of furin. And this is quite important because some cancer patient samples overexpress furin, and there's some evidence that you can get the second cleavage variant in some patient samples with testicular tumour. But the Gen 2 antibody is the pair you need, and interestingly, this ability to recognise AMH and not care about this second cleavage is exactly what Anch reported as being a goal of one of theirs in one of their posters. So that is a good combination of antibodies that recognise AMH irrespective of the primary or secondary cleavage. So how does the Gen 2 assay work? This is going to be very quick. There's the AMH being captured, there's a wash, there's the second biotinylated antibody, there's the streptavidin, and there's the signal, and there's the well. Okay, so we've already had that. What about complement interference? As Marianne quite rightly said, complement interference is absolutely nothing new. This was an interference in the Ortodelphia human AFP assay and its effect on second trimester Down syndrome. That's serious stuff when you have an interference in Down syndrome. They solved it by modification to the assay. In this particular case here, another case, they used EDTA to mop up calcium because calcium is needed for the complement cancer. So we're here, let's do it. There's the Gen 2 plate, there's the C1 sticking on top if it finds the antibodies in the right orientation. And this is much more likely to happen if there's any aggregates in the antibody. And when people use monoclonal antibodies for therapy, they know how prone antibodies are to aggregate. Aggregation can be affected by the osmolarity of the growth medium, the method of antibody purification, the pH it's exposed to, the concentration it's at, how it's stored, how quickly it's frozen, how quickly it's thawed. Antibody aggregates are nothing new, and they can be catastrophic if they allow complement activation. So there's the C3b binding all over. So now come on to how did the complement interference, so we've got all that, we've been through all the complement interference. So basically, when the assay was validated by Dr. Kumar, now at Anch, who was previously at DSL, when it was validated, they wrote a paper in the Journal of Immunological Methods, it's about 2010, said the performance of the assay is ideal for investigation into the clinical role of AMH in men and women. And that was what was thought at the time. And that was what Beckman bought into. And unfortunately, perhaps because of batch variations or whatever, the problem emerged later. So a little bit of defence for Beckman there. So how was the complement issue overlooked for so long? Well, probably the early in-house validation work was done with old samples. The percentage of complement interference in serum samples collected and stored in the same way may be more reasonably constant. I know complement does vary, but I'm not sure I agree with Marianne that it always varies over a huge range. So, and then there's this issue of aggregation. Let's go past that. So how can you avoid complement interference? Minimization of aggregates, variations in assay design, addition of chelating agent. These are just possibilities. This is the paper that Marianne referred to by Bill Ledger, University of New South Wales, confirming that the premix fixes the problem. Premixing serum samples with assay buffers is a prerequisite for reproducible anti-Müllerian hormone assay using the Beckman Coulter Gen 2 assay. And he said, confirms that the premix fixes the apparent storage instability issue, which we now know to have been caused by complement. Now, since this time, of course, other companies have come up with assays, which are now being widely used. Just recently, the same authors presented a paper at a meeting, a big Asian meeting in Aspire meeting, I'm not sure, I think it was in Melbourne, and they had been experimenting with the ANCH assay, and this is the poster that they produced. Is premixing of serum necessary to obtain reproducible, you should say AMH results, using the ANCH Labs AMH assay? And they came to the conclusion, quote, however, a similar premixing effect was also observed with ANCH Labs kit, which suggests the likely presence of serum interference. So, you know, problems can occur. We all have to look after our own assays and try and make sure that they don't have these sort of interferences. But Beckman Coulter is not the only company that has had this sort of issue. What's the only way to avoid assay interference completely? When I set up the inhibin B assays in 1996, I knew nothing about assay interferences. Every serum sample I tested had an interference. I didn't know what to do about it. So with the help of a collaborator that sadly has now died, Shanti Muthukrishna, died this year, she came up with the idea of a boiling treatment. So we add STS to the sample we boiled. And that will remove all known false positives, complement, heterophile antibodies anyway. In the real world, commercial companies can't do that. They like things to be simpler. And so no company should ever claim that their assay is free from interferences. You haven't looked at enough samples, is my answer. And one should always be vigilant in these things. So interferences, automation, why are these so important? This is a little slide which I'm glad William Finch is in the audience. This explains why in the old inhibin B assay it would have been better automated, and why you have to be very careful when you're wording the instructions. Okay, so are there any remaining problems in the AMH assays that I'm aware of? In a nutshell. Firstly, there's no evidence for AMH conformational change affecting patient assay values. There is no evidence for AMH disulfide exchange affecting patient assay values. There is no evidence for freeze-thaw, short-term storage in the cold or at room temperature, or long-term storage affecting patient values. There is no evidence that dissociation of the mature region of the AMH from the pro-region affects assay values. There's no evidence for in vitro AMH proteolysis affecting patient values in either of the Beckman assays. And you have a lot of independent confirmation from Roche about the stability, those of you who went this morning. All the reported problems were caused by complement. So is AMH really stable in serum? Well, this is a quote from the Roche paper. The sample stored at minus 20 to minus 25 or 2 to 8 degrees up to 7 days showed no significant storage. It's a stable analyte. What are the forms of AMH in blood? Well, this paper from New Zealand showed that in human sera, the two forms of AMH, bioactive and non-bioactive, occur in particularly equal amounts. So it's very important to ask the question, what does Gen 2 measure them both? Now, they had a preparation of pro-AMH, which they incubated with furin to convert it to the inactive. So this would be non-bioactive, this would be active. They then measured them in the Gen 2 ELISA. They got a 60% result. But they commented that the authors note that the AMH-NC may have or appeared to have undergone some additional degradation. So we don't know the exact concentration of these. But this was used as the antigen to raise the monoclonal antibodies. Therefore, this must recognise this. Any assay made using an antibody would recognise this best. So when I see it drop to 60%, it tells me that in reality, if the quantitation of these was accurate, then it's seen the two forms equally. How how can one prove that in the absence of better recombinant impurities? Well, Roche solved the problem, because in the blood, plasmin can be produced by adding urokinase. That's how they dissolve clots. Patients who've got clots in the system, they add urokinase. Or by, so what the Roche guy did is he took some serum samples which he'd run in their automated assay, and he added urokinase to one lot and an excess of plasmin to another. And that would then convert all the inactive to bioactive AMH. There was no change in assay values at all. And that confirms that the Gen 2 assay recognises both forms. It measures total AMH. So let's go nearly finished. So what's the appropriate form of AMH to measure at this time? And I'm going to argue total. The reason you should measure total is that all the clinical research studies so far have measured total AMH. Even the two ANCH assays which are available at the moment measure total AMH. The Immunotech very likely measures total AMH. In 2009, there was a French patent application which described a method of measuring bioactive AMH in a sample using the type 2 receptor as one component in an ELISA. I wondered what had happened to that, because I thought if AMH measuring bioactive was really useful, they'd have done something with it. So I phoned up the European Patent Office the other day and found out that the patent had been abandoned. So for whatever reason, they could measure bioactive AMH but found it of no use at all. And then there's the paper by Pankhurst et al., which suggests that the bioactive and non-bioactive forms circulate, but in similar proportions, i.e. equal amount in men, women and boys. Now if something circulates in more or less 50% of the total AMH in men, women and boys at different ages, it doesn't sound as though it's doing a great deal. And then the other thing is that plasmin-like proteases are widely distributed around the body in extracellular tissues, so it may be that the AMH in the blood can all be cleaved as its target organ anyway, and there's abundant evidence that the expression of the AMH gene is controlled by hormones and vitamins, and there's no need to control it at the level of cleavage. So total AMH is the thing to measure. So what are the other assays in the marketplace? I've only got about 4 more slides. The other assays out there are the Roche assay you heard about this morning with the same antibody pair. There's the Beckman fully automated, which you've just heard about. ANCH so far has 2 commercial human AMH assays. One is very sensitive, sensitivity in the order of the assay you've just seen, the automated Beckman. Assays for bioactive AMH. There's a paper recently by a group in Australia using some ANCH antibodies which appears to measure bioactive AMH. But here's the interesting thing, is that how do all these assays compare? I've never seen so many correlations in the literature for one assay in all my life. Old GSL with Gen 2, Gen 2 with old Gen 2, new Gen 2 with ANCH with Roche, Roche with Beckman, and they'll be starting to compare with assays for FSH next. I mean, it's going on forever. So anyhow, this is the final thing I think illustrates my point, is that this is a paper recently published by David Robertson in the US using 2 ANCH assays, one for total AMH, one for bioactive AMH, 200 and something samples, perimenopause, land normal women, and he measured that, and there was a correlation coefficient of 0.984 between the 2 assays. This is telling you that for whatever reason the percentage of bioactive is almost exactly the same in every sample they tested. The other interesting thing from that same paper, in terms of AMH being constant through the menstrual cycle, when you look in the perimenopausal region, which you'll be able to do with the new Beckman assay, is AMH constant in the cycle? There are so few follicles, you can see the follicular wave. Look at this. So the presence of more sensitive AMH assays is going to pose new challenge. You may not feel as confident in interpreting AMH when you see that what is happening in the perimenopause. So the areas for research are to make sense of these low values. Can useful information be derived from them? And on the bioactive side, somebody's got to prove to me that the measurement of bioactive AMH provides any different information from the total AMH assays. Very reliable, very sensitive, which you're going to get from Roche and Beckman. Thank you.